don't build buildings that aren't straight, right? So we're looking down this long hallway, and there's lights on the ceiling.
Yep.
When you look down that hallway, does the floor appear to ramp up towards your eye level, and does the ceiling appear to ramp downwards towards your eye level as it gets further away?
Yeah, to a point.
Yeah. So in reality, is that ceiling that's above you physically going downward, or is it just a matter of your perception due to perspective?
No, but I don't think that's a large enough scale to see. Like the hallway would have to be quite long, wouldn't it?
Wouldn't even have to be that long.
Uh,
I mean, that's what you
to
see.
be able to see it. Well, yeah, yes, because
have you ever been in a hallway where you don't see the ceiling appear to come towards your center view, and the floor appear to go up towards your center view? That's how you view everything. Always. It's perspective.
Well, I don't think there'd be the hallway long enough to show it not. You know what I mean? Like, unless the hallway is like, so if you had a hallway that was from where you are standing to the ship, that could be really far. I don't know how far ships are bend across the horizon. I'm not sure about
that. Dude, if you had a hallway, so let's talk about that. If you had a hallway, if you look at the live stream voice text, you'll see an image of a hallway that's running as a GIF, and you'll see the effect in question.
Oh, yeah?
Okay, so if you had a hallway, the length all the way out to a ship where a ship starts to disappear, which is roughly 3 miles, 3 to 4 for a 6 foot tall observer if he was on the shoreline. If you were looking down that hallway, right, after a short while, the rest of the hallway would be unresolvable. And all you just see is everything converging to a point, and you'd be impossible to see the rest of the hallway.
I agree with that. But
right. So if you then remove the hallway, does the same angles of light not apply anymore?
The ship isn't the same as a hallway because
why not?
The ship is a point, if you know what I mean.
Right. So remember what I just said.
You know what I mean.
Remember what I just said. The angles of propagation within the hallway and the angles that they enter your eye or the optic, right, are at too small of an angle to be resolvable on the hallway, which is approximately the same height as a person, right? And all of the information from the end of the hallway recedes into a point. So if you then remove the hallway, would not the same thing be happening to the portion of the ship that occupies the same space as the hallway, being approximately 7 to 8 feet tall, standard hallway? So at
isn't a ship bigger?
3 miles. I'm talking about the portion that represents the same scale as the hallway, like I just said. 6 to 8 feet.
But how am I supposed to see that point from a ship that's far away? I wouldn't be able to see that.
You got it. So what you would see by what you just admitted is you wouldn't see the portion of the ship that represents the same scale as the hallway, but you would see the portion of the ship that is much bigger, being the top. So by your own admission, you generally conceded that the bottom of the ship would disappear due to the laws of perspective alone.
The point of the ship that faces, you know what I mean? Like the point of the ship that is level with me.
Right, that part's going to disappear.
Obviously,
first.
The whole length of the ship isn't the same size as
but
the whole.
Think about this.
Stop there for a second. Hold on, stop there real quick, because he's saying something that most Globers don't get, and that it's worth noting. Okay, the whole ship represents a certain angular size, but each portion of the ship represents a different angular size, and the smaller portion at the bottom of the ship subtends a different angle than the whole ship. And due to the law of triangles, that angle is going to be smaller. And since we see in angles, once the angle gets too small, we won't be able to resolve the bottom of the ship while still being able to resolve the top. Thank you for being one of the first people to get that without having to go for 2 hours. All right, I yield the floor.
Yeah, that was a really good point. Just think about it for a minute. If the floor all the way up to the vanishing point, and at the vanishing point, that's where you can't discern the floor anymore. Of course, his feet or the bottom of the ship at that point cannot also be discerned when it's connected to that point on the floor. Do you get that?
Oh, wait, so you're trying to say that it's like a plane? Like, I don't know if, like, so every part, so, right, so every part is the, sorry, I'm a bit, like, I understand what you mean, but every part of the ship. Sorry about this. Can you just
Yeah, so
say it?
think of it this way. If you had a smaller ship, like a dinghy, just a little boat, that was tied to the side of that ship as it goes away so that you can see it. And you see this little ship. Now, if you removed the big ship, you understand that that smaller ship is going to visually disappear at a shorter distance than that large ship because it's a smaller object, right?
Got less height.
Yes, less height. So you would expect the little dinghy to disappear before the large ship, solely just based off of its height, right? Because you understand perspective works. The angle is going to be too small for you to resolve that small ship first. Now imagine tying that dinghy to the large ship and sending it out. It would stand to reason that that small ship is still going to be unresolvable at the same distance, regardless of whether it's tied to the ship or not tied to the ship, right?
Agreed.
So as that little dinghy disappears because we can no longer see it due to angular resolution limits of our eye, it's tied to the ship. Wouldn't it stand to reason that the whole entire portion of the ship that is that height would also be unresolvable?
Yes, because in my opinion, it's gone under the horizon, but I understand what you said.
Okay, perfect. So your claim would then be that the only reason that things disappear from view is because they're being physically obstructed by Earth curve. Would you agree with that?
Yes, on long enough distances.
Okay, perfect. So now I do this on the regular. I go to my little lake, 333 meters across from the observation point to the observation, which is a yellow floaty boaty on the other side. Okay. Now you put that into the math of the alleged curvature of the Earth, and you will find that the heights that I observed at, there is no way that the Earth curve, if it existed at all, could be precluding that boat in totality. Okay. So this means that it's not geometrically possible for the curve of the Earth to obstruct that boat. Yet, okay, 9 out of 10 times I go, pretty much consistently, the entire yellow boat disappears. So, my friend, what is causing that to happen?
Sorry, so it's 333 meters, right? How big is the boat?
It's about
How
half a
tall
meter,
is the
one and
boat?
a half feet. It's about 1.5 feet tall.
Okay, well, let me do some maths. So how many? Sorry about this.
Just doing the math up the top of my head, AI, no portion of that boat should be hidden. And if it is a portion, it's such a small portion that you wouldn't be able to notice based on the Earth curve calculator. Because that's what, about a quarter mile?
Right.
It's 1.2 miles. No, sorry, 0.2 miles.
Quarter of a mile.
Yeah, 0.2 miles. Sorry. All right, so
do you know what the alleged drop over 8 inches per mile squared, right?
Yeah.
Right, so that would be at the surface.
So then it would be like 1.6.
1.6 what, inches? Would be the alleged hidden height due to the curvature of the Earth, allegedly.
Mm-hmm.
So when AI said he goes out, and 9 times out of 10, the whole entire boat disappears. Why? Is that Earth curvature? Do we have a tiny Earth? Smaller Earth?
That'd be funny. Probably not.
I'm so glad you said
there's no reason.
Right, so then what must be the reason? Okay, so it looks like it's happening. So what must be the reason?
The only other hypothesis you've given is that most of our vanishing points.
Well, let's just be more broad, just for fairness' sake. Okay, it's not because of geometry, it's because of an optical effect of some kind, whatever that might be. It's no longer in the category of geometry, it's in the category of optics, correct?
Yes.
Exactly. So now that we've agreed that the bottom of things can be missing, or an entire object itself can be obstructed without the necessity of Earth curvature in the way, we can now make progress.
Oh, sorry, I'm sorry, it's really late here.
Now, I want you to realize that that's a necessary concession that you made because it's obvious, because it's observable, that it is not true, that the only way for things to disappear from the bottom is because of Earth curvature. So that's a false statement.
You've proven that to me.
Yeah, I just did, and you conceded. So if you retract now, it just means, you're fair, exactly. Now, you might argue that those effects are this or those effects are that, but we know for certain that it falls in the category of optical effects. Now, since we can't do this for real right now, we're going to do this in our minds, right?
Okay.
And mental experiment, okay? So, well, first let's preface this. Do you know that the optical device, whether it be biological or synthetic, has a limit to it, known as the angular resolution limit? Everything that has an angular field of view has this limit. It's just that simple. It's a hard physical limit. It's known as the Rayleigh criterion.
I heard of it.
Yep, it's known as the Rayleigh criterion. So for the human eye, it's approximately 0.02 degrees. Okay, what that means is that any light from the source that enters below that limit will be interfered with by any other light that enters within that angle. And therefore, there will be no resolvable information, and it can at best be only rendered as essentially, for lack of a better term, 1 pixel value. So you imagine
resolution.
Yeah. 1 pixel value, meaning 1 element, right? 1 element of the total picture that you're seeing.
But
so in that area,
everything have different
in that
resolution.
angular area.
Sorry.
No. This is angular resolution, not pixel density. So for example, if you only had 4 pixels in your sensor, right?
Mm-hmm.
If you literally had only 4 pixels in your sensor, you could never render something that requires 10 pixels to render, correct? It would look like blurry nonsense, would it not?
Yeah.
Exactly. So now you fully understand the principle. So if you imagine a man standing on a line looking out, right, and these radials, right, of angles emanating from his eyeball, you can imagine the 0.02 degree triangle coming out from his eye and going out along the horizontal line in front of him until it intersects the horizontal line. And so you have a triangle, right? And I want you in your mind to color that triangle red. Now, everything that enters that triangle must, of a necessity, render as one color value in the final image, which we've already agreed. It just so happens that if you take the time right now to map this out, it pretty much coincides with where the alleged horizon is for a 6-foot tall observer. The triangle hits the horizontal line approximately at the same distance. Very coincidental, don't you think? So principally, we know this to be true. So, for example, let's say that you're standing over water, and then you have a brick, but it's not a solid brick, it's a floaty brick. And let's just make it red, because red is very bright, easy to tell apart from blue. So if you take said brick, and we've already established that this water is horizontal, okay, it's not curving in any way, it's perfectly horizontal. That's the premise. You might even imagine that it's a floor, painted blue rather than water, make it easier. So you take said red brick, put it on the floor, and you have your friend start to walk away from you. Now, as he keeps walking away from you, something interesting is going to happen. Eventually, you will not be able to see the color red anymore, because the red and the blue simultaneously will occupy less than 0.02 degrees. And as they approach that towards 0 degrees, the blue and the red will meld together into purple. And then it will meld together to where you only see the air and the blue floor, and you can't even tell the purple anymore. Now,
that makes sense.
Let's just say, for example, that you call your friend, you say, okay, I can't really see the red thing anymore, so you can stop pulling. And your friend goes, okay, and he stops pulling. Now what your friend does is he calls his other friend, who brings over a truck full of red bricks, and he starts stacking the bricks on top of the previous brick that you can't see. He stacks 1. You start to see a very faint purple. He stacks 2. The purple intensifies. He stacks 3. You start to scratch your head and say, I'm starting to see red. He stacks 4. Now you see some more red. He stacks 5, 6, 7, 8, 9, 10. And now you see a line of red. But when your eyes trace down this line, as they get closer and closer to the floor, eventually you cannot see the bottom of the stack. It has become unresolvable. It has disappeared. Rest assured it is there, and it is the bottom portion of the stack. But the stack in total has disappeared from the bottom, has it not?
I like that. I do like that, yeah. I really do
this
like
is a
that.
necessary, yeah, you're right. And this is a necessary consequence of the way our eyes work. And and all optics with an angular field of view, by the way. In order to see without perspective, truly, you need to have a lens the exact size with all available propagation angles to a parallel rate to the target source from the object. So if you want to observe a 100-meter building, you need a 100-meter lens, not an angular lens, but a straight lens that only allows the light to pass collimated, parallel, and horizontal to the sensor. So you need a 100-story tall sensor and a 100-story tall collimated lens. Okay, these types of optics don't exist. So every observation that we make is through an angular field of view with these limitations, in which we already have said that because of optical phenomenon, the bottoms of things can disappear. And that's just the facts. All right, so with that, I rest my case on that, unless you have any questions specifically.
Why would you need a 100-meter lens to see 100-meter thing?
You need a 100-meter lens to see a 100-meter tall building without the effective perspective, and it needs to be a collimated lens where the sensor exists parallel to the light coming from the object.
Like a mirror.
So if you don't have such a lens and you use normal lenses like your eyes, you'd be standing on the ground, right? And the angles of propagation from the top of the building would be at a downward angle towards you, forcing all of the light from the propagation angles to enter at essentially inverse angles after they pass the lens, and that's what creates the effect of perspective. Is that you see an angle.
Like a mirror. Oh, this is right. I'm imagining like a mirror, right? Okay, and this mirror is the same height as something. Yeah, right. So it's like a mirror, if you know what I mean. It would work like a mirror.
Yeah, well, the problem is that mirrors suffer from a perspective as well. If you stand in front of a mirror and start to walk away from it, does the image that appears to be you not shrink in size? Of course it does.
Yeah, because that's your eyes. It's not the mirror.
Right, because your eyes are getting the angled light, not the straight light, not the direct one-for-one parallel reflection that's going back in on itself. So now you get it.
Mm-hmm.
There's also another way to show it. The ancient Greeks, of course, didn't have any fantastic telescopes or anything. They just looked at the horizon with their eyes, and they drew on a piece of paper and used orthographic view to assume that the horizon was Earth curve. So in orthographic view, things don't get smaller with distance. So the mountain is just as tall angularly in their idea, in their math, but that's not how it is in reality. It's actually tiny in reality, and so when they compare these pictures from reality to their math or orthographic side view, which they got from the Greeks, they're actually just taking perspective and turning it into Earth curve and assuming that the horizon is this start of this Earth curve. But there's no evidence to actually substantiate that.
So with telescopes, you have a more resolute lens. Not lens. You know what I mean?
Yeah. With a bigger aperture, you can see further, like in the black swan images and other such things. That's why we use telescopes, to see further. And then if you use a very small aperture, like we did with the pond tests and other stuff, such things, we can see that the horizon appears much closer and things disappear over what should be a flat surface. According to the globe mechanics, these bodies of water should not have enough convexity to hide these objects, but it does happen on the smaller aperture cameras. But on the bigger cameras, you can actually see the boat still. So it is optical. There's no Earth curve here.
What's black swan? I know what a black swan is, but what is black swan experiment?
A black swan is not an experiment. It's a reference to the Karl Popper's falsification, and he has a story that goes with it. You can say that all swans are white, and people can just accept that. But if you find a black swan, you know that all swans are white is just wrong. There are black swans. So that's what we find. We find black swans that show that all swans are not white. And so the black swan image is just what this image was called. It's two oil rigs taken. A snapshot taken from a video where he lowers the camera 1 foot off the surface of the water, So the horizon should be only 1.22 miles away on the globe, but we can see the horizon way past the second oil rig, so that's over 10 miles. The size of that globe is completely unsustainable, so it just doesn't work.
Black Swan. Excellently well said, Grace. Go ahead.
So it's basically just a proof, a contradiction.
Yeah, we're comparing the claimed globe geometry to reality, and it doesn't hold up. But you can go check it out. You don't have to just believe anybody here. You really should go out and see if you can test some of this stuff on your own. If you have a body of water nearby that's like 5 miles, 10 miles big, maybe bigger, that's a good start. Next time you go on vacation to the beach or something, take an Earth curve calculator with you. See if you can do some long distance observations. This is the kind of stuff you don't want to just leave this Discord and be like, well, these guys on Discord told me it was flat. Like, you want to go out and check for yourself. So, there's plenty of resources for you to be able to go out and do that. And if you need help, we're here.
Okay, so let's establish where we've come from so far. We've conceded that the concept that the Earth curve is the only reason why things disappear from the bottom up is false. Right? Now we've been presented with the black swan, which is a premise, right? In a sense. That premise is that if you can disprove a certain proposition by providing one counterexample, that negates the proposition and the proposition isn't true. So the proposition in the idea that we already agreed to isn't true is that the horizon is a hump of Earth curvature between point A and B that's blocking the bottoms of things. Now, we've already agreed together that that's not the case. Now, let's talk about the black swan. In the black swan photo, the horizon, as you can clearly see by looking at the photo, is beyond the oil rigs. Right? The oil rigs are at 9 miles, respectively, between the other one and the other one. There's approximately 9 to 10 miles from the shore. This means that the horizon is greater than 10 miles. We only know this because we see the boats. Sorry, not the boats, the oil rigs. So we know the horizon is beyond 10 miles. And as he said before, it must be, if the Earth is a globe and if the horizon is a geometric hump of Earth water, right, that's curving and getting in the way. From the observation height that the man observed this, it should have been at 1.225 miles. It's not at 1.225 miles. So the necessary conclusion is that the horizon that you see is an optical phenomenon, not a geometric edge of Earth hump curved water. Now, in summation of all of this that we've already discussed and you conceded to, okay, is that there is no hump of Earth curved water blocking the bottoms of things. Now you might say, okay, that's compelling. How would I know for sure? Well, the correct answer is to directly measure the water. So far, we've been talking about optical defects, right? So let's measure the water. How are we going to do it? We can't use a string because of the catenary curve problem, right? Which is a physics problem. Just take my word for it. Can't use a string.
Okay.
Can't use a solid piece of steel for similar reasons. So the most efficient means to get something at that range, that we need a sufficient sample size, right? So what's a sufficient sample size? Let's say 25 miles. That sounds pretty good, don't you think?
25 miles, you'd see. Doing the maths. 25 times 8. 200 inches, which is what? I don't know what that is in feet.
25 miles, it would not be 200 inches.
Wait, what? So wouldn't it be 25, then 8 inches per mile, times it by 8?
It's squared.
Oh, there we go. So would it be
If you were
5?
doing it your way, it'd be a
5
slope,
times.
not a curve.
Oh, yeah, that makes sense. Sorry. Right, so 5 times. What is it again? What is it? 5 times 8?
It's 20.
40.
No, 25. 25 times 25
Uh-huh.
times 8 inches.
Right, so
That'll give you inches.
sure.
5,000.
That's going to give you. Right, that's going to give you the drop.
16 feet.
Right, so that's 416 feet drop. Right.
That doesn't seem very believable to me. I'm gonna be honest.
Really?
Yeah.
Why not?
I don't know. I don't think you can see 400 feet of drop between 25 miles. That's like.
I mean, that's the math of the ball.
Significant. That's very significant.
Yeah, it's very significant. I mean? So we have something that's 400 feet, right? 400 feet.
I can live with like 400 inches, but I can't live with 400 feet.
Well, too bad, because that's the measurements of the ball that they told you exists.
Yeah.
Okay, so I'm going to walk you through it. So this is how it goes. You got 400 feet. It's actually worse than that, but we'll just use 400 for sake of argument. It's easy to divide. So what they did is they went, set up what's known as a laser transit measurement. Laser transit is basically a really long level, right? Because obviously you don't have a 25-mile long level. So you level the laser on the one side of the land, you shoot it over 25 miles of water, and you have a target, right? You set up the laser at 6 feet off the ground. You set up the target at 6 feet off the ground. Right?
Can't a laser be refracted and stuff though?
Ding, ding, ding. He said it. He said the word.
Oh, what? Hey. Shh. Calm down.
Oh, okay. No.
We're not getting frenetic here. Yes. The correct answer is lasers can deviate due to refraction. Okay. So I want to ask you this before we start. You already have heard this is a 400-foot differential, right, between the drop.
Mm-hmm.
Now,
yeah,
we're going to measure this. We're going to measure this to see if that drop is there by setting up a laser transit level. Now, I'm going to continue with how this works, okay? So we'll set a baseline for how this thing's supposed to function. So in construction, let's say you have a foundation, so you have a piece of land. You set up the laser on one side, you set up the storyboard on the other, which is what the laser hits, and it tells you the differential between a level laser and the ground. So for example, if I set up my laser at 4 feet tall and the storyboard says 6 feet, right? Then that means I have to add some dirt to level the ground, right? And transversely, if it says in the other direction, I have to take some dirt away. So what this tells me is over my foundation that I'm trying to lay, whether or not I'm laying it flat. Because I can go with that storyboard and get 4 feet here, 4 feet here, 4 feet here, 4.5. Uh-oh, I got to change something. Right?
Yep.
Now, of course, there's tolerances, right? So when, for a client, I want to make a level floor or a level foundation or a level piece of land, there's tolerances that they're willing to accept. Now, dirt has a different tolerance that someone's willing to accept, in concrete has a different tolerance that someone's willing to accept for their tile in their kitchen floor. right? They want that floor flat. They don't want it curved, they want it flat. So I want to ask you